we have to prove Bernoulli's theorem. For that, we have to consider a pipe of variable cross section. This is the pipe of variable cross section. These are the two centers of this pipe. We can denote the ground. We can denote the ground. This is the ground above which the pipe of variable cross section exists. Two ends of the pipe are x1 and x2. The end x1 of the pipe is at height h1 from the ground. End x1 of the pipe is an altitude h1 from the ground, and the other end x2 of the pipe is at the height h2 from the ground. Pressure, liquid pressure at the end x1, that is P1, is greater than the pressure at the other end x2, that is P1 is greater than P2. As P1, liquid pressure P1 is greater than P2, that's why liquid flows from the end x1 to x2. Liquid flows into the pipe with velocity v1, and the liquid emerges from the pipe through the end x2 with the velocity v2. This is what we can denote liquid flow of liquid towards right through the pipe. In this way, liquid emerges from the pipe. So you can denote the direction of liquid flow. Liquid flow occurs towards right. It enters into the pipe, and liquid flows out of the pipe from the end x2. From the end x2. Let P1 and P2 be the liquid pressure or pressure applied on the liquid. P1 and P2 be the pressure applied on the liquid at the ends x1 and x2 of the pipe of variable cross section. A pipe of variable cross section. As P1 is greater than P2, comma, the liquid flows into the pipe at the end x1, which is at the lower height h1 from the ground. The liquid flows into the pipe with the velocity v1 at the end x1, and it emerges with the velocity v2 from the end x2 of the pipe. A1 and A2 are the area of cross section of the two ends x1 and x2 of the pipe of variable cross section. A1 and A2 are the area of cross section of the two ends of the pipe. According to equation of continuity, that is A1 V1 is equal to A2 V2, as A1 greater than A2, so V1 less than V2. Hence, liquid flows with a greater velocity V2 at the end x2 than the velocity of liquid, that is the velocity v1 of liquid at the end x1 of the pipe, and the kinetic energy increases due to flow of liquid through the pipe from its end x1 to x2. Also, potential energy of liquid increases. According to work energy theorem, work done in pushing the liquid will be equal to increase in kinetic energy of liquid, under bracket closed, plus increase in potential energy of the liquid when the liquid flows from the end x1 to x2 through the pipe of variable cross section. increase in potential energy of liquid as it flows from the end x1 to x2. That means work done in pushing the liquid will be equal to increase in kinetic energy of liquid plus increase in potential energy of liquid. Liquid flows from the end x1 to x2 and height of the pipe from the end x1 to x2 increases. That's why potential energy increases. And we get work done which is equal to increase in kinetic energy plus increase in potential energy, or comma W equal 1 by 2 mv2 square minus 1 by 2 mv1 square plus mgh2 minus mgh1, or comma P1 minus P2 into V. Work done is equal to change in pressure into volume. P1 minus P2 into V equal 1 by 2 m V2 square plus 1 by 2 small m V1 square plus small m GH2 minus m GH1, where small m is the mass of liquid. Small m is the mass of liquid which small m is the mass of liquid which is pushed through the pipe of variable cross section, where m is the mass of liquid of volume capital V which is pushed through the pipe x1 x2. M is the mass of liquid of volume V which is pushed through the pipe x1 x2. Now we can draw the diagram again. This is a pipe of variable cross section having two ends x1 and x2. We can denote the centers of this pipe. x1 and x2 are the two ends of the pipe. P1 and P2 are the liquid pressures at the ends x1 and x2. As P1 is greater than P2, liquid flows towards right with a velocity v1 and liquid enters into the pipe with a velocity v1 and the liquid emerges with a velocity v2. Here we can denote the liquid flow in this way. Small m and capital V are the mass of liquid and volume which is pushed through the pipe due to pressure difference. Small m is the mass of liquid and capital V is volume of liquid which is pushed through the pipe. Liquid flows in this direction from the end x1 to x2. Liquid flows in this direction from the end x1 to x2 of the pipe. And the two ends, in this case work done, W is the pressure difference into the volume. Pressure difference into the volume of liquid which is pushed through the pipe. Therefore, work done W will be P1 minus P2, which is the pressure difference between the two ends of the pipe, into V. Capital V is the volume of liquid. Here P1 and P2 are the pressures at the ends x1 and x2. P1 minus P2 is the volume and V is the volume. P1 minus P2 into V will be equal to the work done. This is the work done in pushing the liquid from the end x1 to x2. Or comma P1 minus P2 into V. P1 minus P2 will be equal to 1 by 2 m by V V1 square, m by V V2 square minus 1 by 2 m by V V1 square plus small m by capital V GH2 minus small m by capital V GH1. We can keep increase in kinetic energy and potential energy under bracket. So P1 minus P2 is equal 1 by 2 rho V2 square, where rho is the density of this ideal liquid minus half rho V1 square bracket closed plus under bracket rho G H2 minus rho G H1, where rho is equal to m by v mass by volume, which is the density of the ideal liquid which is flowing through the pipe x1 x2 due to pressure difference, or comma p1 plus 1 by 2 rho v1 square plus rho g h1 equal p2 plus 1 by 2 rho v2 square plus rho g h2. So this is the expression of Bernoulli's theorem, and we get P1 plus 1 by 2 rho V1 square plus rho G H1 equal P2 plus 1 by 2 rho V2 square plus rho G H2, or comma P1 by rho plus V1 square by 2. So this is the expression of Bernoulli's theorem and hence proved. Also, you can explain or describe what is P1 and P2. Here P1, P2 are the liquid pressure at the ends x1 and x2, and they are also pressure energy per unit volume of liquid at the ends x1 and x2 of the pipe. 1 by 2 rho V1 square, 1 by 2 rho V2 square are the kinetic energy per unit volume of liquid respectively at the ends x1 and x2 of the pipe respectively. Half rho V1 square, half rho V2 square are the kinetic energy per unit volume. Similarly, rho G H1 and rho G H2 are the potential energy per unit volume of liquid at the ends x1 and x2 of the pipe respectively. P1 and P2 are liquid pressures, and they are also known as pressure energy per unit volume. Therefore, pressure energy plus kinetic energy plus potential energy should be equal to constant. That is, pressure energy per unit volume plus kinetic energy per unit volume plus potential energy per unit volume will be constant. That is, P plus 1 by 2 rho V square plus rho GH equal constant. P plus 1 by 2 rho V square small v square plus rho GH equal constant. So this proves Bernoulli's theorem. That means sum of pressure energy, kinetic energy and potential energy per unit volume of liquid which is pushed due to pressure difference remains constant. That is Bernoulli's theorem. Additional information, we can draw the diagram again. This is a pipe of variable cross section. These are the two centers of this pipe. We can denote the ground. The two ends x1 and x2 of the pipe are at the heights h1 and h2. P1 and P2 are the liquid pressures at the ends x1 and x2. As P1 is greater than P2, liquid flows towards right with the velocity v1. Liquid emerges with the velocity v2 from the pipe at the end x2. Two ends x1 and x2 are at the heights h1 and h2. Here height increases. Two ends x1 and x2 are at the heights h1 and h2 from the ground. P1 is the liquid pressure, and it is also pressure energy per unit volume of liquid at the end x1 of the pipe. Liquid flows in this direction as shown in the figure. Small m and v are the mass and volume of the liquid which is pushed through the pipe. Rho is the density. 1 by 2 rho v1 square at the end x1 is the kinetic energy of the liquid per unit volume. Kinetic energy of the liquid per unit volume. Similarly, we can denote potential energy. Rho G H1. Rho G H1 is the potential energy of liquid. Potential energy of liquid per unit volume of liquid which is pushed through the pipe. Rho G H1 is the potential energy per unit volume of liquid at the end x1. Now P1 plus half rho V1 square plus rho GH1 will be constant. We can add pressure energy per unit volume, then kinetic energy per unit volume, and then potential energy per unit volume, that is P1 plus 1 by 2 rho V1 square plus rho G H1. That is the sum of three types of energy per unit volume. Remains constant. Similarly, at the other end x2, P2 is the pressure energy per unit volume. P2 is also the liquid pressure, and it is also known as pressure energy per unit volume of liquid at the end x2 of the pipe of variable cross section. And liquid has the kinetic energy per unit volume at the end, x2. 1 by 2 rho V2 square is the kinetic energy per unit volume of the liquid at the end x2 of the pipe. Kinetic energy per unit volume of the liquid. Similarly, at the end x2, rho gh2 is what? Rho gh2 is the potential energy. Is the potential energy per unit volume of liquid which flows through the pipe. And if we add rho gh2, P2 and half rho V1 V2 square, we get P2 plus half rho V2 square plus rho gh2. That is the sum of pressure energy, kinetic energy, and potential energy per unit volume remains constant. That means total energy remains constant. This is the total energy of liquid at the end x1, total energy per unit volume at the end x1, which was P1 plus half rho V1 square plus rho G H2. Liquid flows from the end x1 to x2, and this two total energies will be same because sum of three energies remains constant. So finally we get P1 plus half rho V1 square plus rho GH1 equal P2 plus half rho V2 square plus rho GH2. This is additional information or explanation of Bernoulli's theorem. This is the mathematical expression of Bernoulli's theorem. That is sum of pressure energy per unit volume, kinetic energy per unit volume, and potential energy per unit volume remains constant. Again, we can explain the diagram in this way. Liquid flows into the pipe x1, x2 with a velocity v1, and it flows out of the pipe with the velocity v2. Two ends of the pipe are at the heights h1 and h2. Liquid flows in this direction, in this way, from the end x1 to x2, from the lower end to higher end. If the liquid flows from the end x1 to x2 of the pipe of variable cross section, number one, pressure energy per unit volume decreases, pressure energy decreases, kinetic energy increases because area of cross section decreases, and potential energy also increases. Pressure energy decreases, but kinetic energy and potential energy increases. V1 is the velocity with which liquid flows into the pipe at the end x1. The end has area of cross section A1. At the other end x2, area of cross section is A2. As A1 is greater than A2, V1 less than V2. So kinetic energy increases if liquid flows from the end x1 to x2, and the heights of the two ends are h1 and h2. The end x2 is at the higher altitude h2, as h2 greater than h1. So potential energy of liquid also increases if liquid flows from the end x1 to x2.